All right, so let's see if we can find a formula for the vector projection of B onto A. Again, we're going to assume that we're working in the case when the angle between A and B is acute. The formula that we find works in all cases, but it's a lot easier to see why it's true and where it comes from in this case. So if you just look at this triangle and realize that this is actually a right triangle, then you know that, well, for example, the cosine of theta is the length of this side over the length of that side. The length of this side is the length of the vector projection of B onto A, which we labeled C. So this is exactly, cosine theta is C over length of B. And what that means is the length that we're after, C, is exactly length B cosine theta, where theta is the angle between A and B. Now, you might recall that A dot B, we learned A dot B is length A, length B cosine theta. So I can actually solve for cosine of theta by dividing both sides by length A, length B, and then use that. And so what that means is this C that I want, the length of proj of B onto A, is exactly length B times A dot B. Whoops, let's get rid of that. A dot B over length A, length B. And of course we can cancel one of those length B's. That's kind of messy. So I get A dot B over length A. All right, I'm going to mention in passing that the reason why this formula holds all the time is actually this C should really be absolute value. It's assuming to be positive. In our picture, it's always positive. In the other pictures, it could be negative, and that's coming from the fact that the dot product could be negative. But since we're assuming the angle is acute, then we know that this dot product is positive, so C is positive, and everything works like we planned. So it turns out that that is the length of the vector projection of B onto A. And so we can now write down a formula for the vector projection. So here it is. This is the formula that you'll need to know. The vector projection of B onto A is this A dot B over length A times the vector A divided by length A. I can hear some of you groaning, even though this is a video. It is what it is. We can at least combine these two guys. Let's do that. So if you wanted, you can write this as A dot B over length A squared. By the way, length A squared is A dot A. So one version of this formula is A dot B over A dot A, whatever. But the point is that we get the vector projection of B onto A is this formula. You know what? I don't like that box. Let's make it bigger. All right, so there it is. That's the formula that we've been seeking. And like I said, this formula works in any of the cases above. But if you look at the case that we did, then it's a lot easier to see. So one more definition, and then we'll do an example, and then we'll be done. So definition, so I want to briefly mention the scalar projection. Some of you were saying, whoa, I thought we're done with projections. Well, the scalar projection of B onto A, which we're going to denote, you know what, let's just say is. We usually write it comp B onto A. Now the word comp might conjure up some memories of classes that you've had. That's not what we're talking about. There's no English stuff here. This is just standing for component. This is the scalar component. And so what on earth are we trying to say? Well, comp of B onto A, it's just that same C that we came up with before. It's A dot B over length A. And your book actually, I believe, says that this is the length of the vector projection. It's not quite right because length, at least in my mind, should not be negative. And this can be negative. So here's how you think about the scalar projection. The scalar projection is the C that you multiply A by to get the vector projection. It's the constant that you're multiplying A over length A by to get the vector projection. So we went back up and we said, hey, look, the vector projection is C times A over length A. That C is the scalar projection. So it's literally talking about the same projection. You have the vector, and then you have, in our case, for the picture we drew, the length of that vector, but it might be the length of that vector flipped. And so, well, that's where this comes in. So scalar projection is just A dot B over length A. So those are the two formulas that you need. You need to know proj and comp. And now let's practice doing these. So I would invite you to pause the video and go ahead and compute the scalar and vector projections, and then I'll do them with you. All right, so if I want to talk about, let's first off do the scalar projection of B onto A. I like to start with that because once I have the scalar projection, then I can get the vector projection a lot easier. I know my formula, this is just A dot B over length A. And so this is going to be what? This is going to be 3 plus 12 minus 6 over 9 plus 36 plus 4. And so this is, 9 over, this is a length, sorry. This is a square root of that. 40, 49, so 7. So this is just 9/7. So the vector projection works out here. By the way, it's very rare that you get a clean radical here. Usually you're stuck with a radical downstairs. Whatever, not a big deal, but it does work out in this case. All right, so that is the scalar projection. I'm done. Now when I want to write down the vector projection, so I have the vector projection of B onto A, I know this is going to be A dot B. Actually, we can say it like this. It's going to be the C that I just found, 9/7 times A over the length of A. And so this is going to be 9 over 7 times, well, let's see, it's going to be the vector A, so 3, 6, negative 2. And then I'm going to divide this whole thing, if you will, by the length of A. The length of A we got to be 7, so I get 9 over 49 times 3, 6, negative 2. So that's the vector projection of B onto A. All right, so we'll stop here. You've got everything you need to do to knock out the homework, and I would encourage you to do that.